Hello everyone, this video is final presentation for our final project of course CS 5800. My name is Jingyi. My group members are Qinghang and Jiaoyue. Our project is optimal route planning in daily life. I want to introduce a little bit about the background of our project. We want to solve a real-life problem of making optimal route planning when we plan to go to multiple places from our home and then return our home. This real-life problem is actually traveling salesman problem, which is a very well-known problem in theoretical computer and operation research. The standard version of TSP is a hard problem to solve and belongs to the NP hard class. Then I want to introduce the motivation of me and my group members of why we want to choose this project. For me, that's because I'm living in California, where towns are sparsely distributed. So it takes us a lot of time on the way when commuting or shopping and picking up food in the restaurants. Although we can easily add multiple stops in map apps, the current map apps won't optimally design the sequence to travel all the stops we entered. Sometimes I take a detour, so I spend extra time on gas on the road. I always hope to have a way that we can just enter the places we want to go, and the map app can automatically design the optimal sequence to travel all the stops.
So for project task and assumptions, we decide to use 3 different algorithms to solve it and compare it. The first one is the most intuitive one, brute force algorithm. It's going to try every possibility and find out the optimal solution. The second one is a dynamic programs algorithm. This one focuses on figure out a subprogram, and in order to get out the final solution, it comes out with a correct result with faster speed. And the last one is MST algorithm. This MST algorithm comes out with an approximate result with a faster speed. Next, please. Yeah, so before we really started implement these 3 algorithms, we do some abstractions for the problem. First of all, we decide to use a map to store the coordinate of each locations. This will make it easier to calculate the distance between different locations. Then the way of representation between 2 addresses, we choose to use edges. Then for each location, it would be a vertex. And we decide to use to calculate the Euclidean distance between 2 locations for our calculation benefits. Yeah, so next part, we're going to do some analysis and comparison between the 3 different algorithms. The first one is the brute force algorithm. For brute force algorithm, we took all the vertices, which are the locations in this graph, and we took them. We consider each 2 pair of the locations have an edge. So this graph will be a complete graph. And because it's a brute force algorithm, we'll do DFS for each possible itineraries. And finally, we're going to compare the cost of each itinerary and choose the least expensive one.
Yeah, next we can go to the dynamic programming algorithm. The high-level solution of dynamic programming algorithm for this problem is not difficult to define. For every location X in our visit plan, other than the start point, we define the minimum cost path from the start point to that location X by visiting all locations exactly once. Let the cost in our problem, we define the cost as the distance. Let the cost of the path be cost X, and the cost of the complete trip would be the cost X plus the distance from position S to the start point. So finally, we return the minimum of all the cost X plus distance X to start point value. Next page, please. So we can tell the subproblem of this problem from the previous analysis, that is finding the minimum cost path from the start point to that location X and visiting all locations exactly once. We define the term DPIS with the cost of minimum cost path visiting each location in set S exactly once from the starting point and ending at position I. S is a subset of the visiting of the set of all the locations we want to visit on this trip. And the recursion rule is DPIS is the minimum of DPJ S minus I plus distance JI, where J belongs to every node in S with J not equal to I and J not equal to the start point. We start with the minimum subset, which only have the start point and another point, and gradually increasing the size of the subset of increasing the size of the subset to solve this problem.
And next, I will talk about the minimum spanning tree analysis. For this algorithm, we want to just loop to every location once, and then which is the MST algorithm to solve. For the first step, we build a minimum spanning tree of the graph, and go to the second step. We use the DFFs to traverse each location and then build a graph circle, and then we calculate the total path, and that's our final result for the minimum spanning tree algorithm. And for the comparison, for the minimum spanning tree analyze, the runtime is the big O of E log V, when the E is the address number and then V is the location vertex. And for the comparison, as we can see here is the 6 stops, which means the 7 vertex. The brute force and the dynamic program have the same result, which is correct, and then the dynamic program algorithm is faster than the brute force, and the minimum spanning tree is the most fast, but with the approximate results. And for the 11 stop, which means the 12 vertex, the dynamic program and brute force is also the same result for the shortest path length, and the dynamic program is much faster than the brute force. And then as we can see, the minimum spanning tree is also faster than the dynamic program, but the result is the approximate result. And I will pass to my group member to talk about our limitation and future plan.
Yes, there are some limitation of our project given the limited deadline and workload we can offer on this project. We made several assumptions and simplicity in our project. So first, we simplify location to only have a name and an XY coordinate. We exclude the consideration of other factors such as opening time of that location, etc. And we use Euclidean distance between 2 points as the cost of path between them. Therefore, the path in our problem is a complete and directed graph. These assumptions are too idealistic and not going to be the case in real life. Second, the data we use to test our system is artificial. We basically manually create the data to test our system. Third, there's no user interface in our project. To use our system, the user need to clone the code and run a script on their local machine. In the future, we could, there are some plans in the future we could do to refine our project. So first, we could integrate our project with Google Geo tools. So the location could be real life locations, and the cost of paths could be real-time got from Google Map apps. And the definition of optimal could also be extended to the shortest time, the best traffic route, or by different transportations. We will also provide a user interface so the user could easily use this system.
Thank you.
Yeah, that's all about our presentation. Thank you.